Hello bachcho and welcome back. Today we are going to learn a very important topic from Unit 11, which is dual nature of radiation and matter. And that topic is the photoelectric effect. Now this is a concept that is absolutely crucial for understanding modern physics, and I promise you, this simple, exam-safe explanation will clear up all your doubts.
Okay, before we dive into the physics, let's start with a little puzzle. Something you might have actually wondered about. Why is it that a weak, kind of dim ultraviolet lamp can give you a nasty sunburn, but even a super powerful, blindingly bright red lamp won't? It just doesn't seem to make sense, right? Well, keep that question in your mind, because by the end of our session today, you'll know exactly why this happened.
So to solve our sunburn mystery, we first have to go back in time. We need to look at a moment when physics faced a huge crisis, a time when the old, trusted theory of light it completely failed to explain what was going on. You see, for hundreds of years, everybody was absolutely sure that light was a wave. And why not? It made perfect sense. A brighter light? Well, that's just a wave with a bigger amplitude, which means it carries more energy. Kind of like how a huge ocean wave has way more power than a small ripple. This was the classical wave theory, and honestly, it explained almost everything. Almost.
But here's where things got really weird. When scientists actually did the experiments, the results were shocking. The wave theory predicted one thing, but reality showed something completely different. First off, the old theory said that a brighter light, a bigger wave, should knock out electrons with more speed and more energy. But nope, the experiment showed that brightness had zero effect on the electron's energy. What mattered was the color of the light. Second, the theory said any color of light should work as long as you make it bright enough. But in the lab, they found that you needed a specific starting color, a threshold frequency, or absolutely nothing would happen no matter how bright you made the light. And finally, the old rules predicted that if you used very weak light, there should be a time delay, right? For the energy to build up. But guess what? The effect was instantaneous. The wave theory was just totally wrong on all counts.
So physics was properly stuck. The best theory they had was failing badly. And then along came a young patent clerk you might have heard of, Albert Einstein. He came up with a revolutionary idea that changed everything. Let's see how he cracked the code.
Einstein's idea is actually pretty easy to understand with a simple analogy. Imagine you're trying to get into a concert, okay? And there's a strict bouncer at the door with a rule. You have to be a certain minimum height to get in. This height requirement, that's like the light's frequency. Now, it doesn't matter if you show up with a huge group of 100 friends. If none of you are tall enough, well, none of you are getting in. The size of your group, that's like the light's intensity, or its brightness. You just can't make up for a lack of height by bringing more people along. Simple, right? And this is the real heart of Einstein's idea. He suggested that light isn't some continuous, spread-out wave. Instead, it's made of tiny, individual packets of energy. He called these packets photons. And here's the main point, the one you absolutely must remember. The energy of a single photon depends only on its frequency, that is, on its color. A high-frequency violet photon is packed with energy. A low-frequency red photon, not so much. So, this brilliant idea led to his famous photoelectric equation. Let's not get scared by the symbols, think of it like this. A photon, carrying an energy packet of HV, comes in and hits an electron. Now, to escape from the metal surface, the electron has to pay a kind of energy cost. This cost is called the work function. It's like the ticket price for the concert. Whatever energy the electron has left over after paying that price, well, that becomes its kinetic energy, the energy it uses to move around. So the crucial point is this. The final kinetic energy of the electron is just the photon's starting energy minus the work function it had to pay to get out. And here it is, that beautiful equation in its final, clean form. The maximum kinetic energy of that escaping electron is equal to hv, the energy of the photon that came in, minus w, the work function of the metal. It's simple, it's elegant, and it explained every single experimental result that had puzzled scientists.
But a great theory needs great proof. It's not enough to just have a good idea. And the experimental proof that came from scientists like Robert Millikan was, well, it was absolutely undeniable. It proved, without a doubt, that Einstein was right.
So first, the scientists measured the maximum kinetic energy of the electrons. They used this clever technique called stopping potential. Basically, it's just the voltage you need to apply to stop even the fastest electrons from reaching the other side. And what did they find? If they kept the color of the light exactly the same, this stopping potential did not change at all, no matter how bright or dim the light was. This was the proof. Intensity doesn't give electrons more energy, it just means more photons are hitting the surface every second.
Okay, so next they checked what happens when you change the frequency. They plotted the electron's maximum kinetic energy against the light's frequency. And just like Einstein's equation predicted, they got a perfect linear relationship. As the frequency of the light went up, from red to yellow to blue to violet, the maximum kinetic energy of the electrons also went up, in a perfectly straight line.
And here is the most amazing part, the real clincher. When they calculated the slope of that straight line graph, what did they get? They got a number, and that number was a precise value for Planck's constant h. This value matched perfectly with what other scientists had found in completely different experiments. This was it. This was the final, undeniable proof that the photon model was correct. It was a cornerstone for the new world of quantum physics.
Okay, let's switch gears for a minute. I really want to talk about some very common mistakes that students make in their exams on this topic. These are what I call silent killers. They can make you lose marks without you even realizing it. So please, pay close attention.
This is by far the #1 misconception. I see it all the time. It feels right, doesn't it? Brighter feels like more powerful. But in the quantum world, this idea is completely wrong.
So here is the correct way to think. A simple line I want you to memorize for your board exams. Ready? Frequency is the gate. It decides if an electron can even escape. Intensity is the flow. It decides how many electrons escape per second. Making the light brighter just gives you more electrons, not faster ones. Please, remember.
All right, the second common mistake comes from accidentally using the old wave theory logic. Many students think that, okay, if you shine a weak red light for a really long time, the energy will slowly build up and eventually, pop, an electron will come out.
But that's not how it works at all. Remember this, the interaction is always one photon to one electron, and it happens in an instant. A red photon? Think of it as an energy weakling. It just doesn't have enough energy to pay that work function ticket price. You can send 1 billion red photons, 1 trillion of them, but not a single one will be strong enough to do the job.
So, as you can see, the photoelectric effect was so much more than just explaining a weird experiment. It literally forced us to accept a completely new and frankly pretty strange reality about what light actually is. So, let's quickly summarize.
Okay, here are the key takeaways for your exam. Point 1. Light is made of these discrete energy packets called photons. Point 2. A photon's energy depends only on its frequency. Point 3. The photoelectric effect only happens if the photon's energy is greater than the metal's work function. Point 4. Intensity controls the number of electrons, while frequency controls their energy. And finally, point 5. All of this proves that light has a dual nature. Sometimes it acts like a wave, and sometimes, like in this case, it acts like a particle.
And that leaves us with one last really fascinating thought. We started this journey thinking light was a wave, and we've just proven that it can act like a particle. This discovery turned physics completely on its head, and it opened the door to the next logical question. If a wave can act like a particle, then could a particle, like an electron, sometimes act like a wave? Well, that's a story for our next explainer.